All right. Good morning, everybody. Happy Wednesday. And This is actually sort of the last class before Halloween. So I guess I'll go ahead and get into the Halloween spirits. So let me just, for a second, just do a simple gag. There we go. I can go ahead and teach class like this for the rest of today. So I think I could probably pull it off, but I guess I can kind of see from these polls right there. So I guess I could teach class like this the entire time, but I think this would be a little distracting. So I'll probably just go ahead and just take it off. But I guess happy Halloween, everybody, or happy pre-Halloween, I guess is the right term. So I'll probably be running around campus with a panda mask today. So hopefully nothing really too bad happens, I guess. Hopefully I don't get attacked or anything. So yeah. All right, cool. So at least that's we're in the spirit then of Halloween, and the semester is actually getting close to the end as well, which is also kind of nice. So definitely all good news. And Assignment 4 is on the works of being graded, so I have checked on it. So it's not graded, but it's kind of in progress. So I'm gonna try to like see if we get those graded pretty soon because I guess you guys want to know your grades obviously at some point. So also some more good news, or I mean, if it did run correctly, your threads, I guess, obviously it would be okay. But let's say if anything happens, say when it's graded and you felt that it was too harsh, let me know. I can, of course, double check the assignments once they're fully graded, of course. So there's that. So anyways, go ahead and go back to actual lessons. Let's go over last time's content and go ahead and continue from that. Let me see. Share screen one. Okay. So basically, from last time, we actually covered hashing. So this was the last example we did was double hashing, and basically double hashing is when you have two hash functions, and we use that to kind of hopefully the purpose of that is to avoid sort of or try to have our elements sort of not clustered together in the table. So really with hashing is all kinds of ways you can mix and match. You can mix open addressing with chaining. You can have multiple hash tables. You can do all kinds of tricks to try to map your elements in a way where you avoid clustering and collisions. But these are very simple, basic open addressing methods: linear probing, quadratic probing, and double hashing. So I'll go ahead and I'm just um, going to just sort of finalize all of these, and then we can go ahead and move on to our next data structure. So we only have really two more data structures left. We have priority queues and graphs, and we're sort of done. So that's kind of good news, actually. We're definitely getting towards the end of material for the class. That's all good. So let's go ahead and just that. So anyway, I guess I guess I'll call this open addressing conclusions. So we have these sort of three basic ones we use, which was linear probing. We had also quadratic probing. And we also had this double hashing. So we had these three main ones. Of course, you can um, combine these and do all kinds of other sort of techniques, but those are the basic ones we have. So linear probing, let's go ahead and sort of compare and contrast these. So the positive is that it's very easy to implement. I mean, really, it's nothing to it, really. It's just all we do is if you have a collision, we just go to the next element until we finally find our key or until we finally find a vacant spot. Nothing really too complicated there. But then downside is that, well, we have clustering, and clustering is bad because that sort of gives a higher probability to have collisions because you have one big target in your hash table. So it gives a better chance of having collisions if you have different keys with similar index values. So it's really creating one big, area that can cause a collision. So that's kind of bad. But I guess the benefit is there's nothing to it to implement it. Double hashing, the positive is that, I mean, doesn't always guarantee to avoid clustering, but I guess attempts to avoid clustering, or there's a better chance as long as your hash functions are decently written, the better chance to avoid clustering because you have two hash functions, so it's not very deterministic or not really predictable as to where elements will sort of map in your table. So it lowers the chance of having collisions, or sorry, clustering, which will eventually, if you don't have a lot of clustering, then you have a lower likely of having collisions in the future. But downside is that's going to be it's harder to implement because you have to create two hash functions. So it's going to be a little more complex. You can even have multiple tables as well, multiple arrays for it. So it's going to be more of a complex structure, which is a downside. But then the benefit is you try to really avoid clustering and try to minimize your collision amount. And quadratic probing really is kind of, I guess I'll just say the best of both worlds, I suppose. As in, it's kind of neither linear, neither here, neither there. So it's better than linear probing because it doesn't have so much clustering, but not as good as double hashing. It's harder than linear probing, but not as difficult to set up as double hashing. So it's kind of neither here nor there, sort of. So it's easier than double hashing, but not as good. And it's going to be better than linear probing, but not as hard as double hashing. So it's kind of like really, yeah, best of both worlds, I guess is the right term to use for this. So that's the overall concept there. Also, I'm not going to compare these with chaining method. I mean, chaining method, you can compare these also with these open addressing in general. But chaining really I guess the real difference of chaining versus, I guess I'll put these here as well. So chaining versus open addressing is that chaining has less options to handle collisions. Whereas open addressing has more options. We have several options to handle collisions, so open addressing has more options. It's more options to handle collisions. So I guess for chaining though, however, the table can never really ever be filled up because you can always add more elements to the linked list in that particular index of your hash table. So technically, you never really have to resize, although it wouldn't be a bad idea if you have a lot of elements chained in one area of your sort of your table linked list. You want to resize your table to hopefully spread everything apart, just like we do for resizing for open addressing. So you might have to go through every element one by one and sort of remap it to a larger table. Same method as we resize sort of our open addressing version of our hash structure. So it doesn't hurt to do that, but technically you'll need to if you don't want to. Whereas open addressing, you have to resize because there's no linked list there because what happens, the table is full, then you will be probing forever and never be able to actually ever insert something into your table. So training does not need to be resized, but it's recommended, of course, if load factor is high and open addressing, you definitely have to resize. But either way, though, you want to resize no matter what. If you have around 50% load factor, you want to resize. Load factor, remember, is just sort of the ratio of items over your actual table size. So if that gets kind of large, you want to resize. And of course, the last comparison, which will be, I guess, sort of hash map versus a tree search, which we'll just go ahead and use AVL tree. Right now, there's actually more types of search tree structures than just AVL trees. AVL tree was like the best one we went over in this class. So the real benefit, real compare and contrast, the hash map has an O of one sort of find, insert, delete sort of runtime. So it has a very fast lookup time. Whereas AVL tree is O of log n. Do our find, insert, and of course we can go over deletion, but you can do a deletion on AVL tree as well. You have to first find the elements, remove it, and you have to do some work to kind of fix the tree afterwards. So, hash map could be O of n if it's a very high load factor, and if let's say the keys happen to all be mapped to the same index. You can of course resize your table. Also, you don't have, I guess you resize your table as well. So there's ways to avoid that. So ideally, a hash map is supposed to be a constant lookup time. But then the benefit or the anti-benefit of this would be have a large, so I guess table size, the structure size, sorry, the structure size is probably a better term. Structure size is much larger than the amount of elements. And then for an AVL tree, um, the structure size is the same as the amount elements. So basically, AVL tree, we have exactly as much nodes as we need. So we don't have to have extra space. So then, okay, fine. So hash map in a search tree structure. So for typical problems that are not very huge data set amounts, the hash map is a better approach because if your computer can handle the amount of storage, then you get a fast runtime. So if you use unordered map or dictionary for Python, it'll be a fast lookup time. AVL tree is a little bit slower, or any kind of search structure is a little slower. So really, a search structure like an AVL tree or a different type of tree structure, tree search, is mostly used for like databases, where you have a very big data collection already as it is. So you can't afford, typically a database could have maybe a few terabytes, could be used even more than that, could be used to store all the data in a database. So using up more storage to have extra empty spots to search is going to be not a good idea because you're already at 2 terabyte capacity at this point. So you really don't want to have more space. So for databases, typically a tree traversal, maybe kind of hash and tree traversals kind of are mixed together, but the tree structure is like the main sort of advocate for databases, where the hash map is mostly for doing some application does not really require database. So you have all your data in memory already, then of course, then you can use a hash map for that. Let's see. Yeah, so your operating system, I think for cache memory, it will some have a hash mapping structure. It maps to somewhere on your hard drive, so it'll be faster lookup time. So on your CPU cache, I believe that's where you use some type of a hash type structure, the quick lookup element, lookup in your memory, essentially, main memory or hard drive. I think main memory is what it uses for mostly. So it'll look up main memory very quickly using a cache, which is stores the most recent stuff you've looked up already, so you can very quickly go back to that same location in memory to access something. So a hash map is used, I believe, for cache memory on your CPU, I believe. I'm not really an expert on computer organization, architecture stuff, but I think that's the idea. So yeah. But in general, though, for bigger storage or bigger data collection, a tree traversal is mostly used for smaller set. It'll use a hash map. That's I think that's sort of the benefits. But of course, for any applications you write, even for competitive coding, even for interview problems, even for we work somewhere, typically a hash map is mostly used to look up things quickly. But for actual big data collections and database or such, then a tree structure is mostly used for that. So that's kind of compare and contrast with them. So really, I guess it comes down to hash map or tree structure, which is more important, time or memory. There's a trade-off, obviously, there. So hash map has a better lookup time, but you sacrifice memory for this. Tree traversal, you save memory, but then you have a slower runtime. So it depends on which one's more important for you right now. Is memory important or time is important? So that's sort of the idea there. So that kind of will conclude hash map. So assignment 6, which is already on the way, which is unordered maps. Hopefully the assignment is coming along nicely. I'll have a new assignment up next week, which will be creating your own custom hash map. And I'll sort of not create a very complicated or nothing that bad. So there won't be any array of linked lists for the hash map structure. Just going to be sort of going to be using sort of open addressing, double hashing, but a little bit different than the ones we've covered, but nothing that's impossible to grasp or to, work out. Maybe the code is always, of course, coding is always different and, it's always hard to code stuff, but conceptually, though, it shouldn't be too bad to understand how this hash map is going to work. But I'll have that posted up by the weekend. I'll cover it in class next Monday. So let's go ahead now and go over our next structure, which will be priority queues. Okay, so a priority queue. Well, in CS 202, you might have learned about stacks and queues, so LIFO stacks and FIFO first in first out queues. Well, a priority queue is kind of similar to that. So basically, it's going to be a container class is the idea, just like with a stack or queue. And what happens as any type of structure, you have to be able to implement sort of insert, I'll write this a little nicer, insert and remove. Just like for a stack or a queue, you have this push and pop or enqueue, dequeue. Well, same idea. You have to have this insert and remove type of functions you have to do with this. So it is going to be an abstract data type. Obviously, as I put this over here, it's actually an abstract data type, or you can abbreviate this to be ADT. So just like a stack and a queue is also an ADT, a hash map could be considered abstract data type as well. It just basically means that we can define this data type sort of without writing code. We can kind of define this type in general. So really, a priority queue can be implemented in Java, C++, Python, any language, because it's not really, doesn't depend on the language really. So we can sort of define this data type sort of an abstract way, not really literally writing code. We can just talk about this without code to understand the concept of how this structure works. So basically what's going to happen for this priority queue is, as always, we're going to insert an element to the back structure. We're going to remove an element from front of structure. And the difference with this, it looks almost like a queue so far. The difference is we insert something when element is inserted, it can potentially uh, up in structure. So think of, I guess, a queue, a first in, first out queue. It's like a line at the store or a line in any kind of in a line in a bank, wherever, it's a line. So if you're the last person in line, you're the last person to get served. The person in the front of the line is first to be served. Whereas a priority queue is more like a hospital line, I suppose. So if you enter a hospital, but your condition is more serious, you move up in the line. That's how hospitals work. That's how it should work. That's how it does work. So basically, based on some priority value, we're going to move it up. I'll put this here based on some priority value. So that's really how this works. And we're going to do this operation known as a bubble up and a bubble down to move elements up and down the queue. So we'll go over the actual technical details in a second on this. Once again, so ideally here is that we will use, so we're going to, so we use an array to maintain the items. The idea is that we will sort of, but then the array essentially is going to, I say it's going to emulate a binary tree. So yes, I know binary trees are back, but I'm not going to use sort of that pointer node notation. I'm going to use an array to essentially emulate or mimic a binary tree. So the idea for this particular instance of a binary tree using an array, the way we're going to actually work this out is that the root item in the tree will be at index 1. So we're not going to use index 0 for anything because I guess it's sort of simpler kind of to, I guess simpler to sort of, how shall we say, do the math in our head, I guess. So index 0 will be kind of a wasted spot, but it's okay. Wasting one spot's not going to really be the end of the world, so don't worry about that. Index 1 is going to be where our root item is going to be in this structure. And then for each index I in the array, we can go ahead and use the following formulas. So the parent is at index I divided by 2. So since I is going to be an integer type, and so is 2, this is going to be an integer division. So it's going to be the floor of I divided by 2. So if I is 5, then the parent will be at index 2. If I is 4, that'll also be index 2. So index 4 and 5, those two nodes, parent is going to be at index 2, basically. So we can very easily compute the parent index of a node. And of course, the left child is at index 2 times I, and the right child is at index 2 times I plus 1. So it's kind of looks kind of familiar to one of our recent assignments. So we use this array version. Yeah, just like in the homework. There we go. So this is kind of, I guess, an array can be used to maintain a binary tree. In fact, for assignment 5, we could have not even used the binary tree, could have had an array, and just use that to jump around. We could have done pre-order using this array and not have to do any type of insert tree creations, but the purpose was to actually, work on binary trees. So yeah, I know it's kind of a bummer, right? We didn't have to even do that, but I did that just because to get us to have an assignment that involved binary trees. That's kind of, unfortunately, we didn't need to do that, but I guess for the sake of this class and the structure of 302, for the sake of that, we have to do that. That's there we go. So I'll say it like that. We didn't really need to, but because we're in school, we needed to. So yeah, that's life. That's school and that's life. So yeah. So so that's basically how we do this. Yeah, same performance because it will take one extra sort of you have 11 elements and you have to traverse pre and post orders. We do one extra O event operation to build your tree. So it will take one plus one extra O event work, which will complexity wise will still keep the process keep this runtime O event. So it would not hurt the runtime at all. Just yeah, it's just more work, but same runtime. It's pretty cool. In fact, I guess yeah, I'll just keep it at like that for even algorithms actually in general. Sometimes having a lazy structure gives you a better runtime actually, which is really weird, right? It's weird how in algorithms doing more work will not hurt your runtime, and sometimes being lazy, having a lazy algorithm can actually give you a better runtime in certain situations, which is really kind of weird. It's interesting. That's more of a 477 concept. So anyway, um, so that's basically how we can emulate this. So let's go ahead and just sort of map out or sort of kind of write out our sort of priority queue structure. So I guess before I do, I'm going to go ahead and just do one last bullet here. So for a priority queue, we typically use sort of a min heap or max heap is used to implement a priority queue. So I'm going to just go over min heaps mostly today, but min and max heap are very similar. So for a min heap, um, parent node is less than both of its children. So a little bit different from an AVL tree. So we don't have this where the left is smaller, right is larger. No, for mini heap, both children will be larger than the parents. The parent is always less than both children for a mini heap. So therefore, put a dash over there. The root contains smallest element um, in the tree. Makes sense. So what happens is, you could always prove this inductively that if let's say the parent's always going to be less than both children, as you go up the tree, you can prove inductively that the root is going to, or you can use some type of a explanation you can create that you can prove that the root has to be the smallest element in the tree. So for max heap, same thing except different, as in the parent would be larger than both children, and then the root would have the biggest element among all the elements in their tree. So max heap is not much different from min heap, very similar. But I mean, I'll go over max heaps when we go over heap sort. But for right now, though, when I do the examples today on heaps, we'll use a min heap just because there's no real difference between them. So if you understand min heaps work, max heaps, you understand that too because they're not different in a sense. So now let's go over actually how to implement this structure. So basically, it'll be a templated sort of type as always. So favorite concepts in 302 is templates. The templates in C++ are great because they give you these ginormous errors for doing something really small, which will definitely freak you out. And it's, yeah, templates. I don't know why they're like that in C++. But anyway, though, a template. So we're going to have a type, and we're going to essentially, I'm going to just sort of not have the entire class, just sort of write out the details of how we can implement this structure. So we're going to have basically an array. I'll call it sort of heap array. It's a regular one-dimensional array, no point, no linked list, no array of linked list, just a very ordinary, peaceful array. Nothing drastic, because linked lists, as soon as that comes up, then that's when things get really terrible suddenly, which I guess it can be intimidating when you first learn about linked lists. So, but anyway, no linked lists here, just regular ordinary arrays. And then we're going to have int size and int capacity. So this is actually a little bit of a recap from CS202. So remember, for dynamic arrays, so this pointers type star heap array is going to be a dynamic array. And we have this capacity field, which is going to be the max size of the heap array. So it's going to be the sort of the size set, sorry, the amount of elements, sorry, the amount of elements heap array store. And then size will tell us how many actual elements have been inserted. So size will tell us how many elements there are actually in the heap. And the capacity is going to be the max elements that heap array can store. So at some point, if size equals capacity, you have to resize your array. So remember, because in C++ with dynamic arrays, there's no way of telling when you hit the end. So having that capacity field will always tell you what index is going to go beyond the array. So size will tell us how many elements we stored so far. Capacity will tell us how many we can store max. So once size equals capacity, and you try to insert something, you have to resize your heap array. And then we're going to, of course, have to have our sort of void insert, and we're going to pass in const type ampersand, which is basically, remember, it's just a glorified value parameter. So we're passing in some element of type, this template type, basically, you're going to insert a structure. Then, of course, you want to have, I guess, maybe get min or get max. So get min slash max. This just retrieves the root element. It returns whatever is at index 1 in heap array. But get min or get max will do. And then void delete min or max, depending on if it's going to be either a min heap or a max heap. Going to run this function is going to remove that min or max element. And the two real main important functions you're going to have to write is going to be bubble up and bubble down. So sometimes it's known as percolate up and percolate down. I like to use the word bubble because it sounds fun to say it. If you say it really fast, you sound like Bing Crosby. Bubble, bubble, bubble up, bubble down. So basically, that integer you pass into it, the integer you pass into this function is the index. So I want to bubble up from this index in my heap array. And bubble down, I want to bubble down from this index. So typically, when you do an insertion, you first insert element into position size, increment size by 1, and you're going to bubble up from index size, typically. I'll put this here. So typically, size index will be used typically for bubble up. Bubble down, index 1 will be typically used. The bubble up is going to happen, so it's going to on insertion. So on insertion, you use bubble up. And bubble down will be usually used on deletion. So you could, of course, pass anything else into it, but for the most part, we're going to always use size for bubble up and index for bubble down. So you're going to have these private and public members in your heap structure, and for the most part, straightforward, except only these two functions here. I think bubble down is the more complicated function, I guess. Bubble up is usually simpler. Bubble down is easy. Insert, get min, delete min, all those are simple. Assignment operator is simple because you only have that one dynamic array. So there's nothing to it. To do a deep copy of two heap objects, it's just basically, how shall we say, it's just basically just a simple dynamic array deep copying. So it's nothing too fancy there. So, and deallocating this, just delete heap array. So it's the rest of that content is pretty simple. The only hard part is really implementing this bubble up and bubble down so you can maintain this priority queue structure. So I'm going to now just sort of go over, I'm going to basically, for right now, just assume we actually have, or actually, I can start fresh on a brand new structure and just go over and I'll go over how insertions are going to work. And I'm not going to go give you the code for it, but I think what I go over right now will definitely help you understand how the code would be implemented for it. It's nothing too complicated, really. So let's do an example involving a binary min heap. So I'm going to go ahead and put a line here to separate this. I think this example is going to be useful because really we're going to go over how to implement this structure. Let's go over an example. Okay. So what's going to happen here is initially we're going to have, I'll have my size will be set to 0. So we first create our object. Our default constructor will just set size to be 0. And then capacity, I'll make the capacity just be 10. It's a good, nice round number. I'm going to have the array of size 10, so I'll put my heap array over here. Going to just that and just so put it like that. I'm going to have 9 sort of lines. So actually, yeah, I'll have capacity to be 10, so it's going to be like this. So 9 lines. Straighter, I guess. Maybe I could try and make this straight. Hold on. I think I could pull this off. Nah, didn't really do anything. Yes, that's okay though. That. And we're going to have our indices. I'll use a red for index. So we have 10 elements over here. This will be our heap array. I'm definitely going to copy this right now, so I don't have to keep on redrawing this every time I simulations. So I'm going to copy it right now just to save myself some time. Okay, so here's going to be our initial heap array. So what's going to happen right now is let's go ahead and insert something into our structure. The way it's going to work is I'm going to go ahead and write right here. So insert 5 into my structure. So whenever we insert, so the way I have it set up is when size is 0, that implies that we have an empty heap. I know our capacity is 10, but we have nothing actually stored in our heap at the moment. So I think I might actually do a little differently here. I'm going to modify this a bit. This might cause confusion later on. I'm going to say capacity for now will just be 9. What we're going to do actually is the following. So if 9 is a capacity, then we're going to actually allocate 9 plus 1 elements to our array because indices 1 through 9 will actually be in our heap array, and 0 is going to be kind of a throwaway item. So our capacity will be 9, which really implies make the heap array actually 9 plus 1, or 10. So that way, just because that index 0 is going to be accounted for. So okay, so that's probably better. At least I got that out of the way right there. So anyway, so if I insert 5, we always going to insert into size plus 1. So size right now is 0. Size plus 1, we're going to insert 5 right over here, just like that. Increment size by 1. And that's all that really happened. Nothing really interesting here because it was an empty heap. So we're going to think of it as we're going to have our tree right below. I usually put a tree right at the very bottom so we can kind of, let me see. So that way we can sort of try to visualize our heap array. So really, we're going to be working through our heap array, our array actually. If you're going to code this, you use the array, but I'll put a tree below as just a way to help us visualize what's going on. Let's go ahead and do more examples of this. That was our first insert 5. Nothing too shocking there. Let's go ahead and just continue. So I'm going to now put in sort of my size, which will now be 1. And capacity will still be 9. Let's do that. I'll go ahead now and just copy the array next to it. So I have to redraw this whole entire thing. Awesome. Good. Of course, we had a 5 over here. I'm going to, still going to be our tree right below. So this tree is not going to be part of our code, but just mostly there to help us visualize. So I want to go ahead and insert 7 next. So what happens is, as always, when we insert, we always assign the value 7 into size plus 1. The size is 1 plus 1 will be 2. We insert 7 right over there, just like that. So if we look at it in our tree form, we're going to actually put 7 over there. If we sort of try to visualize the tree version of this, that's where 7 is going to actually go. Looking at this right now, and of course size now becomes 2. We have 2 elements currently in our heap. And we can see here this is definitely a mini heap order because right now we have only 2 elements in the parent. So in this case 5 is the parent of 7 and smaller than 7. And 7 is a leaf, so it has no children. So this is definitely in heap order, in mini heap order. So we're definitely okay right now. Let's go ahead. Now insert a few elements here and there, and then we'll just have some interesting stuff happen finally. So far it's kind of nothing interesting yet, but we will get there. So I'm going to now draw up the next structure. So size will be 2, capacity still going to be 10. I will just go ahead and copy, I shall paste array right over there. So I'm going to go ahead and put 5 and 7 here. So 5 goes over here. I'll have 5 and 7. I'll just draw these circles there. Okay. So let's see. I'm going to insert one more element that's not going to cause any issues, and then we'll go ahead and we'll start to make this a bit more interesting. So I'm going to just thank you. It's 9. Okay, so now I'll do one more insertion, which will cause nothing and anything interesting to happen, but then we'll do interesting stuff in a second. So let's go ahead and insert one more element into the structure. I'll insert, I'll insert 10. So once again, if we insert 10 to our structure, we always assign this element 10 into size plus 1. So we're going to have size is 2 plus 1, we'll assign 10 right there. size will now become 3. And if you look at it in our tree form, 10 would go right over there to 5's right side. So we can already kind of see that it's going to actually be a balanced binary tree because when we insert into our structure, we always insert in level order like that. We'll do some more insertions so you see that. And again, there's nothing wrong because we see that the parent, 5, is in fact less than both its children. So of course, it's going to be a heap of integer types for right now because integers are simple to use. So it's going to be a heap of integers, but I guess you already kind of figured that. So we have 3 elements in our heap. Now we're going to go ahead and do some interesting stuff here in a second. So now let's go ahead and I'm going to just, once again, copy everything over. So size will be 3, capacity will be 9, and I'm going to just paste our array over here. We have 5, 7, and 10. That. And we can visualize our tree in the following ways. So you have 5, 7, and 10. Okay. So now I'm going to go ahead and insert 6 into this structure. So inserting 6. Okay, so as always, you have to insert 6, insert to the back of our structure. So size is 3. So insert 6 into position size plus 1, or 4. You put the 6 right over there. So in other words, 6 will go right over here, if you look at it in our tree form. So we see right there that we have an issue, because if you look at our structure, the parent of 6 is 7, which is not going to be less than the child, because for a mini-heap, the parent has to be less than both children, but at that level where we insert 6, the parent is actually not going to be less, so we're going to have to do a bubble up. So a bubble up basically means that we compare the child to its parent. Parent is larger, we swap with the parent. So bubbling up means we go into just, I'll use blue over here, we're going to take this 6 and we're going to bubble it up. So 6 moves up, 7 goes down, like that. So the for this element 6 at index 4, we know index 4, its parent will be index 2, because 4 divided by 2, we're going to very quickly find the parent node. The parent node index 2 contains 7, so we have to bubble it up. So 6 goes over there, and 7 goes over there. So if you actually were to code this, you have to compare it to the parent using this very simple formula, and then swap them. And after we're done with that, we have to now check the parent of 6. So for 6, it's index 2 now. So index 2's parent will be index 1 because you divide the index by 2. So 6's parent is 5, which we can see in the array by dividing index 2 by 1, or sorry, index 2 by 2 to get 1. In our tree form, you can see the parent of 6 will be 5, and the parent of 6 is smaller now, so we're done. We don't have to do any more work. So when we bubble up, we move the element up in our queue based on whether it has a, so in this case, the smaller element has a higher priority in this case. So now we have our current sort of heap array at this moment. Let's go ahead and every insertion we have to do is bubbling up to make sure we have everything in its correct position. So in the earlier steps, doing the same exact thing, except in the earlier steps, what happened was the parent was already smaller, so we didn't have to actually do any work. But we always check, after we insert, check the parent. If the parent is actually larger, we have to bubble it up. But here, the parent was smaller than the child, so we didn't have to actually bubble the child up in these two cases. But in this case right here, though, we had to, because we inserted 6, which was less than the parent, so we have to bubble a 6 up. So I have to make sure that we always have the case where the parent has to be smaller than the children. So now our heap is in correct form. Yep. So let's go ahead and just redraw this, and then we'll do some more insertion just to get an idea of how insertion works. So size should be now set to 4. We have 4 elements now in our structure. So I'm going to redraw this. So size is 4. Capacity is going to still be 9, of course. I go ahead now and just paste the arrays. I don't have to redraw that whole entire thing. So currently we have 5, 6, 10, and 7 in our heap array. So we're gonna work really from this array, but the tree is mostly there just to kind of help us. We can kind of see, we can visualize how the structure maintains itself. So that's going to be our tree form right below. Okay. So now I'm going to insert 4 into my structure. Let's say this time, let's insert 4 now. I'm going to insert 4. So obviously 4 is going to be our potential smallest element in our structure. So we're going to have to work with this. So we insert 4. We're going to assign this element 4, or this item 4, sorry, into position size plus 1. Size is 4, so we're going to insert 4 into index 5. The 4 goes right over there. So if you look at in our tree form, 4 is going to go right here. You can see, because we always insert to the back of our structure, we're going to always always going to have our elements in level order like this. So now we have to compare it to its parent. So this element 4, its parent will be 6. And also we can see here, 4 is at index 5. If I divide it by 2, I'm going to get index 2, which is contains the value 6. So we can see that the parent of 4 is 6, which is not going to be less. So you have to bubble this 4 up 1 level. So 6 will go over here, and 4 goes over there. If you look at the array version, you can very easily tell the parent of index 5 is index 2. And we see here that the parent is actually not less, so you have to bubble the 4 by swapping with the parent. And then we're not necessarily done yet. Let's go ahead and continue this process. So now 4's parent, which will be this value 5, as we can see here, index 2's parent will be index 1 because divided by 2. And we see that the actual parent is not going to be less. So you have to, again, do another bubble up action, bubble up. So we have to sort of take the 5 and the 4, exchange them. So again, in our array form, 6 goes over there. Sorry, not 6, 5. 5 goes over there. 5 here. 4 goes up there. And so in this case, we can stop now because we're at the root. So we really have 2 ways of stopping this process. Either if the parent is in fact smaller, then we can stop right there. Or if we're at index 1, that means we're at the root, so we can't bubble up any further from index 1. So there are 2 kind of stopping conditions. So we're going to keep on doing this either recursively or using a loop. Either one will be okay. So a loop will work. Or recursively, you can use it's up to you how you want to do this. Maybe a loop is more preferred. I don't know. It's up to you entirely. But you have to keep on doing this process until eventually the parent is smaller, or you're at the root and then you can't bubble up any further. So let's go ahead now and redraw this sort of heap array after we have this insertion completed. So size should have been updated to 5 because we have 5 elements now currently in our heap. So I'm going to have my size. I'm going to redraw this. So size is going to be 5. Capacity will be 9. I'm going to, again, just paste that table here. So I'm going to redraw this entire thing every single time. And we're going to have the following elements in this structure. We have 4, 5, 10, 7, 6. Let me see, 4, 5, 10, 7, 6. Perfect. And the tree form for this array looks like this. So 4, 5, 10, 7, 6. That's how our tree looks like. So again, the tree is only there just as to kind of help us visualize. But if you were to code this, you'd actually go ahead and work straight from the array. But this tree is just to kind of help us sort of see what's going on. That's the whole idea, just so we can visualize this. Okay. So now I'm going to just, I'll insert, let's say, 7, I guess, into this structure just to kind of mess with this. So I'll do a few more insertions, maybe 3 or 4 more so we can kind of get the full idea here. So I'll insert, I'll insert 7. I already said I was going to insert 7. Actually, I already have a 7, so maybe I don't want to duplicate this. So I'll insert 8. Okay. So now what happens is, as always, we're going to have to assign 8 into position size plus 1. So size is 5, so plus 1 is 6. Insert the 8 right over there. Increment size by 1. Then what's going to happen is if you draw out our tree, 8 goes right there. We can see if you always insert to the back of our queue, back of our structure, we're always inserting in level order. We insert 8 over there. So we can see here that this is going to always be a very nice and balanced binary tree, which is kind of the nice property with heap structures. So now we have to bubble the element up because we can see here that the parent of 8 is 10, which is smaller. So you have to bubble 8 up. Oops. So 8 goes up, 10 goes down. And if you look at it in this form, so 8 is at index 6. Index 6's parent will be 6 divided by 2 or 3. So the parent has to be right there. And we see that the parent is in fact larger. So you have to just simply swap these two. Then we have to continue potentially. So 8's parent will be 4, because we can see here index 3 divided by 2 is going to give us 1. And the parent actually is less. We don't have to do any bubbling up. We can stop right there because there's no work to be done. Because after that, parent was smaller, so you have to continue. So again, there's 2 stopping conditions. Either we hit the root or the parent is smaller and we can stop. So I'll do one more insertion just to kind of create a larger tree, and we'll do some extreme examples, or extreme-er examples, I suppose. So I'm going to go ahead now and just redraw this over here, rewrite this. So size 6, capacity 9, and so we're going to have 4, 5, 8, 7, 6, and 10. Draw the tree below. So we have 4, 5, 8, 7, 6, 10. Okay. So I'll insert one more element that will cause no bubble ups, but then we'll have other examples that will cause a little more chaos, I suppose. So let's go ahead and let's insert 11 next, just because, just to kind of fill out this level. Then we can do more examples in a second. So insert 11. Well, as always, we have to insert the element into position size plus 1 as always. So we have size is 6, so 6 plus 1, 7. Insert 11 right over there. We're just going to go right over here in our tree, as you can see. So we always insert in this nice level order. So we're going to always have a balanced binary tree. Now we have to bubble up, and we check the parent of 11 is 8, and nothing has to be done. We don't have to bubble up at all because we got lucky. We inserted the biggest element, or at least bigger than it's bigger than the parent at least. So we don't have to do any kind of bubbling up. This is definitely in min heap order, where every element, the parent is going to always be less than both children. So we are definitely okay. The two children themselves can be any order. So left child could be larger than the right child. Doesn't really have to have that kind of order, but as long as the two children are both larger than the parent, we have a min heap. It doesn't really matter. Now, between the two children, it could be, I guess in this case right there, from what I see, for let's say for five, for example, five's left child is actually larger than five's right child, which that's okay. And then for four, four's right child is actually larger than four's left child. That's also fine. There's no order to be preserved there. As long as they're both larger than the parent, that's all we have to really maintain. Let's go ahead now and do some more interesting insertions. Let's go ahead now and sort of redraw this. Course size should be set to 7 now. So I'm going to now have my size, redraw this, which actually I don't have to redraw this, but I'll redraw anyway though. Didn't really do anything here. Just for note taking, I suppose I'll just, kind of redraw that structure. So again, just gonna paste this over here. And we're gonna have the following 4, 5, 8, 7, 6, 10, and 11, just like that. I'll draw the tree below. So we have 4, 5, 8, 7, 6, 10, and 11. Oh, circles around it as well. So now I'm going to insert 3 into the structure. So we'll see a little bit more work actually that's going to happen. Let's insert 3. So again, 3 is going to be the smallest element in our structure, but you first have to go through this process. We insert 3 into size plus 1. So size is 7 plus 1 is 8. We insert 3 right over there. But if you look at our tree, the 3 would actually go right here. That's where 3 would actually go, because we always insert in this level order. And if you have this array, see this tree right below is really kind of mimicking or sort of emulating this sort of array, or this array emulates the tree. I don't know how to say that correctly, but the idea is that this tree is kind of one-to-one with this array. So if we insert it to the back, we naturally insert it into 7's left child position. That's just kind of the way it's going to work. So we insert at level order, basically. So now we see, after we insert 3, well, the parent of 3 is actually going to be larger than 3, so we have to bubble the 3 up. So then this will exchange, just like that. So look at our array version. So 3 will be at index 8. So 8 divided by 2 is 4. So index 4 is going to be the parent of this element. Sort of draw somewhat of a straight line would be nice. And we see here that, well, the parent is actually going to be not less than the child. So we're going to have to exchange these. And then we have to continue potentially because, well, we might not be done just yet. So now 3's parent will be 5, and 5 is not less, so we have to bubble 3 up once more. Get to exchange parent and child. So same idea. For index 4, its parent index will be at index 2 because we divided by 2. So you have to exchange the 5 and the 3. Like that. And again, we might not be done just yet because we still have to keep on working because the parent might not be smaller and we're not at the root yet. Let's look at the parent of 3, which is going to be 4. And 4 is not smaller, so we have to again bubble up once more. Again, index 2's parent will be index 1, because divided by 2. We exchange these. And now we're at the root, So you can't bubble up any further. So now we're done. So this was a case we have to go all the way up the tree like this. So this is also a possibility. So of course we can kind of see the worst case, which is modeled right there, but I'll do another example of a worst case scenario, and then I'll be it for today. So I'll do one more insertion, but that was one possible scenario. Let's go ahead and redraw this array along with the tree. So I'll go ahead and I'll just put the size, and I should have put the update size to be 8. Size is going to now be 8. Capacity is going to be 9. And I'm going to redraw that array so it looks a bit more nicer. We have 3, 4, 8. 5, 6, and 11. 7 at the very end. That's correct. 3, 8, 5, 6, and 11, 7. Okay, perfect. I'll draw the tree right below. Try to see if I can. I'm going to go ahead and draw the tree. So the tree is just, again, just there to help us visualize. We're not going to really use the tree for the actual implementation or coding for the array is going to be used for this, but the tree is there just to kind of help us out, help us visualize what's going on. So 5, 6, 11, and 7. That. Now, again, I'll just be consistent, put the circles here. All right. So let's go ahead and do one more insertion. I'll insert 2 in this next example. So I'll insert the last example, insert 2. As always, when we insert into our priority queue, we always insert into size plus 1. So size 8 plus 1 will be 9. We insert 2 right there. Then increment size by 1. We're going to bubble up from index 9. So I guess I should have also said that as well, but hopefully it kind of made sense. After you increment size by 1, we call bubble up. You pass in that size value. So you bubble up from index 9 in the structure. So what happens here is a 2 would naturally go over here. That's the right spot you would go based on the fact you always insert in level order, then 2 would have to go over there. And then we have to go ahead and see if it's less than the parent. In this case, it is. So parent of 2 is 5, which is not going to be less than the child. So you have to bubble this 2 up 1 level. So 2 goes over there. 5 will drop below. If you look at in this array version, this element 2 is at index 9 divided by 2 will be 4. Remember, it's integer division. That's going to be the parent of this value 2. And the parent is not going to be less, so you have to swap these 2 elements. We have to continue, potentially. So we see here that for 2's parent is going to be 4. 4 is not less, we have to bubble up again. So we have to compare it to its parent, have to swap these 2. And again, we're not done because, well, the parent of 2 is not going to be less than 2, so you have to bubble up once more. Goes here, 2 goes there. We again have a min heap. So for duplicate elements, the best thing to do is just, I would say in that case, is don't bubble at that point. So let's say if you have a duplicate in your structure, let's say, and a parent equals a child, then I would just say don't bubble because there's no point at that. You're wasting time at that point. So I would just say if you do have a duplicate, treat that as just, okay, don't bubble up. Just keep it right there. That's probably the best way to implement it. The most efficient way is just don't bubble up if the parent is equal to the child. So anyway, this will be our final example. Let's go ahead and redraw this tree and a heap array. So for next times when we continue on this. So of course now the size equals 9, so its capacity. What would happen from now on, if you were to insert once more, you have to first resize your heap array and then perform the insertion. So you'd have to first resize using the standard CS202, that 4 or 5-step process used to resize a dynamic array, which is that very simple 3 or 4 or 5-step solution. And sort of put this here, so we have 3, 2, 3, 8, 8, 6, 10, 11, 7, 5. So, and I'll go ahead and draw this tree as well, just because. So 2, 3, 8, 6, 10, 11, and 7 and 5. Circles around it, just to sort of be consistent. It's going to be our updated heap. So we can see once again, the parent is going to be less than both children at every single level, except for a leaf level. A leaf level is already inherently, by obviousness, it's going to be already in heap order. So we saw here, for every insertion, we have to bubble up. And in the best case scenario, we can see that if we insert something into our heap, nothing happens in the best case, right? So if I were to insert, say, 9 next into our structure, it would go right below 6, and then it's not going to do any kind of bubbling up. If I insert, let's say, 13 after that, same idea, it would not actually cause any kind of bubbling up. So in the best case, you can hope that inserting, it's going to always insert something where it'll be larger than the parent, so no work has to be done. But in the worst case, however, what's going to happen is we have to bubble all the way from the leaf all the way up to a root. So we want to go ahead and sort of count how many steps will that take. Well, we're going to bubble up the height of the tree number of steps, number of times we're going to do this work. And we can already, you can just sort of believe me on this, or you can prove this, by how if you always insert level order, the height will always be log of n. So a heap will never be worse than log of n height, which means the height will always be log of n. So in the worst case scenario, an insertion will take log of n steps, because we first insert to the back of our structure, and we have to, in the worst case, bubble it all the way up to the root in the worst possible case, which is going to basically take log n steps to do every insertion. So I'll go ahead and I'll sort of formally write this out next time. Of course, I'll formally define that, but it's kind of just a little sort of a preview for next time. So next week we'll go over deletion and other sorts of stuff involving heap structures. Because I skipped 0 because it's easier, I guess, on the math. It's simpler if you have 1. So you have to do 0 plus 1 times 2, just 1 times 2. So it's just easier to kind of sort of work the math out, I guess. At least for me it is. So that's why. There's no real reason why. You could use 0 if you wanted to, but so normally you wouldn't skip it normally. But I guess for us though, it's like, sure, we'll just do that. But normally, I guess if you really want to be very efficient memory-wise, then I guess you could just not skip that. But memory-wise, it's still not so bad because wasting 1 extra space is not going to hurt your time or your space complexity really anyway. But yeah, so that's that. So anyway, I guess that'll be it for today. So I guess take care, stay safe. Thanks for watching. Have a great Halloween weekend. And I guess I'll see you guys next week. Take care.